This picture is showing us the exact same thing I just tried to draw. This boron trifluoride. Remember, boron, way back from when, he can be happy with just 6 electrons. But at the same time, he can accept up to 8 electrons and make that full octet. So when an ammonia comes in, those extra electrons in this unbonded orbital can actually be transferred to boron to create this adduct, this situation where you have a boron trifluoride with a coordinate covalent bond with the nitrogen. Now these are just trying to show, the triangles are showing that the fluorines are coming out of the screen, where the dashes are showing that those fluorines are going back into the screen. And the same thing is true with the hydrogens in this picture. Coordinate covalent bonds are when both electrons come from one atom. It's still a covalent bond. The electrons are being shared, but one atom has to coordinate, so to speak, with the other one to be able to get access to the 2 electrons. It doesn't bring any to the table. It just comes and says, can I get a donation of 2 electrons, please? Complex ions, or coordinate complexes as they're often called because it's coordinate covalent bonding in a more complex situation, are when we have a metal ion as the cation. This happens very often in our transition metals. We get extremely colorful pictures. You can see that down here. Iron, when it's surrounded with water, has this yellowish color. Cobalt, we've already dealt with that. It doesn't show up that great, but this is that pinkish color that we can then push to blue with the cobalt chloride. Nickel makes a green color. Copper makes a blue color. I showed you all in class that ammonia, that silver ammonia complex ion, and we saw that had a very pretty blue color too. And what happens here is those water molecules, those negative electrons on the water molecules are attracted to the iron. We're going to draw a picture to kind of show you what that looks like, and then use some molecule models to see if you can get even a better idea of what is going on. So if we look at our image here, you have this iron, or any metal it could be actually. It doesn't have to be an iron. Most of the transition metals will form these. But you have this iron, and he's got a positive 3 charge, let's say. He's iron 3. And what's going to happen in 3 dimensions, water molecules are going to start surrounding him, lining up those negative electrons. That negative end of the water molecule is going to start lining up all around this iron atom. Of course, there's a limit to the amount of space, only so much iron to go around. But as you continue this in all directions, you'll actually end up with 6 of these water molecules going all the way around the iron atom. 1, 2, 3, 4. I'm running out of room. I don't have as much room as the actual iron would. You'd have to imagine that one is kind of going back away from us, the back of the screen. I'll show you with the molecule in just a second, because this is obviously a little too crowded to have all these waters here. And then one would be coming out of the screen towards us over here. And what all these oxygens are doing is they are saying, sure, iron, you can go ahead and use these 2 electrons. I know it looks extremely sloppy right now. I'm going to show you with the molecules here in a second. If this, we pretend this yellow ball, he is a iron atom. And all of these bonds right now aren't there, but I thought it'd save me some time from clicking them all on there. What's going to happen is the water molecule in 3 directions is going to come in and attach in all these different spots. That big negative end of the water molecule, that oxygen, because it's high electronegativity, is going to be able to attract to each side of this iron atom. And you're going to have 6 different waters around it in 3 dimensions. It's going to look very similar to a jack if you've ever played with jacks. I don't know if that's a game that's still around or not. But very, very similar. Each of the ends of these is going to have a negative end of a water molecule sticking on it. Maybe that'll help you a little bit to see what's going on. Now, here's another example where you have copper surrounded by an ammonium, or excuse me, a bunch of ammonias that are able to, again, each nitrogen can donate 2 electrons. This we're actually going to be able to see a little bit better on the camera, because now we're pretending, get rid of this guy, we're pretending that our yellow guy is a copper ion. And here comes in that trigonopyramidal shape of an ammonia, with that top spot being a pair of extra electrons. And it can donate them to the copper atom and create a bond, and another bond, and another bond. And we're going to get a fourth bond, a fifth bond. I think you can kind of see why it's called a coordinate complex. It's a little complex looking in its bond structure. So now I've got this molecule that is a metal ion, in this case copper, surrounded by a bunch of ammoniums. And then these ammoniums are going to move around, so those hydrogens, remember, they're partially positive charge. It's going to arrange itself in 3 dimensions until we have a situation where we have an entire copper atom surrounded by different ammonias. Depending on the size of this atom, that's how you can determine how many different ammonias or different waters can be attracted to it. But again, you can get an idea maybe holding like that in 3 dimensions what this would look like as we rotate it around. Now, getting a little further into it, once you end up with one of those hydrated might not be the best word, but once you end up with one of those aqua, that's what our list calls them, those aqua chemicals, you can actually end up with hydroxide complexes too. Hydroxide ions are excellent Lewis bases because they can easily, I'm going to stop there because I didn't know what I was going to say with that.